What's up, kids? This is Mr. Carlson, C Squared Mathematics, and today what we're going to be doing in statistics is 5.4a, sampling distributions. What is sampling distributions? Well, it's similar to probability distributions, but just with some stats involved. So remember the last week for Unit 7, when we went through probability, we did a ton of probability distributions. We learned what it was. We learned binomial, geometric, and Poisson. And then we are also going through the first week of stats. We went through the normal distribution. That was a continuous probability distribution instead of a discrete probability distribution. Now what we're going to be doing is a different type of distribution. It's still going to be continuous, but it's going to be heavily involving probabilities, but also involving samples and how we can actually make inferences from the population to this sample. So I'm going to skip bell work. We're going to get right into the objective and essential question. How can I analyze sample means versus population means? We can do that using probability distributions or specifically sample distributions. Okay, we're also going to be asking what is a sampling distribution of sample means and how do you find one? So we're actually finding the sample mean of a sample distribution. What does that mean? We're going to find out. So hopefully you're following along in your note packet. Your note packet is found on Google Classroom 5.a. Now, I will have a whole note packet for 5.4 because we're going to split this up in 2 days. So the next day is just going to be 5.4b. So on Google Classroom, you'll see just the whole note packet 5.4. And we're going to do half of it today, half of it tomorrow. So just make sure you understand that. 5.4a, sampling distribution. What is it? Well, first off, a sampling distribution is the probability distribution of a sample statistic that is formed when sample sizes of n are repeatedly taken from the population. Okay? If the sample statistic is the sample mean, then that means the distribution is the sampling distribution of the sample means. Kind of gets a little bit redundant, right? So basically what this means is we're doing a distribution of sample means. We're looking at the population, the whole. Remember, if MHP is the population, my class is the sample. So we're looking at the population, the whole thing. And then what we're going to be doing is looking at the samples within that population, collecting that data and taking the means, the average of different data sets within that sample, and then seeing how it compares to the mean of the population. Okay, I hope that makes sense. So sampling distributions, consider the Venn diagram here. The rectangle represents a large population, and then each circle represents just a sample size of n. Okay, so I can have sample size 1 or sample 2, sample 3, sample 4. It doesn't matter what the sample size really is, I guess. But notice how some of them are overlapping, some of them are not even touching at all. Okay, it depends on your sample size. Now your population here, these are your variables. What does this variable mean, mu, and what does that weird looking O mean? Now if you recall, my mu, this is how we say it, my mu is going to be my mean. But this is my mean of the population. Okay, this right here is what we call sigma, and this is my standard deviation. So how my data deviates from the mean. But again, this is from my population. Okay, this is from my population. So make sure you keep these in mind because we will start to see something like this. This right here is your sample mean. Okay, so this is your actual sample mean. Okay, and we're going to introduce some interesting different variables as we go on through this lesson. So just keep that in mind. We're going to be introducing other variables throughout this lesson. Okay, but note if the samples are drawn with replacement. So that just means repeated over and over and over again. Then an infinite number of samples can also be drawn from the population. So if I take a sample out and I put it back in, I can take another sample out and put it back in. I mean, this is just an example right here, okay, where I have 5 different samples. But I could have an infinite amount of samples, to be honest with you. within this population, however that size is. Okay, this is just to help you understand. I can take samples out of my population and I can find the mean of that sample. That's what we're going to be doing next. Let's find the mean of certain samples. But before we get to that, let's get into what some of these properties are. Here's the variables that I was just talking to you about. The mean of the sample means x. That should be u sub x, okay, which is this. So this should be x bar, or sometimes what we call this mu sub x bar is equal to the population mean, which would be mu. Okay, so that's very important, which would be equal to the population mean, which would be mu. Okay, there, I fixed it. So the mean of the sample means is mu sub x bar. So x bar is right there. Is equal to the population mean. So what does this actually look like? This means I'm going to take my sample mean right here, and that will be equal to my population mean. So during a sampling distribution, those two will equal. So if I take a sample, a subset out of my population, I calculate the mean number in that sample. That should equal, if I do the distribution correctly, it should equal my actual population mean. Okay? Second, the standard deviation of the sample means, right here, this is sigma sub x bar, is equal to the population standard deviation, sigma, divided by the square root of n. So what does this mean? This means this. If I have sigma sub x bar equals sigma all over radical n. So this is going to be a very, very important formula that we're going to be coming back to over and over and over again. So make sure we know this, because this is how you find your sample standard deviation. Okay, basically the standard deviation of the sample means, so basically the sample standard deviation, that's what it is. The sample, I would just call it the sample standard deviation. How do you find the sample standard deviation? That's how you find it, okay? But you use the population standard deviation there. And then the standard deviation of the sampling distribution is often called the standard error of the mean. So sometimes MathXL will use these synonymously, meaning they will use sometimes the standard error of the mean, but that just means the standard deviation of the sampling distribution. What's the standard deviation of the sampling distribution? The standard deviation of the sampling distribution is that right there. So sometimes this is called the standard error of the mean. Okay? Awesome. So let's erase this. So let's go through example one. I'm going to actually show you how to build this distribution. It's actually very easy if we use Desmos. So I will pull up a Desmos link that you will need to know. But it's simple. It can get tedious, but it's simple. Okay? So you write the population values 1, 3, 5, and 7 on slips of paper. That's the population values. Let's just say there's 4 values for the population on slips of paper and put them in a box. You randomly choose 2 slips of paper with replacement. So you take 2, great, you put them back, take 2, great, put them back. List all the possible samples of size n equals 2. Okay, so this is actually a fundamental counting principle problem, if you don't already know that. It's a fundamental counting principle where we have 4 possible options, but we're taking 2 at a time. So that's actually really just 4 squared, or 4 times 4. So we're going to have 16 possible samples. I'm going to show you that in a little bit. We're going to have 16 possible samples. Okay? And calculate the mean of each. These means form the sampling distribution of the sample means. Find the mean, variance, and standard deviation of the sample mean. So this is the first thing we want to find, and we're going to use Desmos to find this. Find the mean, variance, and standard deviation of the sample means, and we're going to be using Desmos. Compare your results with the population mean, which would be 4, the variance, okay? And then the population standard deviation, which is going to be roughly 2.236 of the population, okay? So how do I write this? I'm going to give this 1 second. Okay. Perfect. Let's put my little face up here, okay? Let's put my little face right there. List all 16 samples of sizes n equals 2 from the population and the mean x of each sample. The mean x bar, really, this is x bar of each sample. So what does this mean? Well, I already told you this is a fundamental counting principle problem, which means I have 4 and then I want size 2, so I have 2 options, but I'm going to choose from 4 every single time. So this means I have 16 possible samples, and that's exactly what it says here. 16 possible samples. We're going to find the mean of each, okay? We're going to find the mean of each. So let's do that. Okay, so continued, I'm given this, all right? This is what I'm given. This is what I'm given. I have 16 different options here. If I counted this, this is 1, 2, 3, 4, 5, 6, 7, 8, and then 8 on the other side. So the 16 possible options. Now the cool thing is I'm giving this to you as a table. Sometimes I won't give this to you as a table though. Okay, so sometimes you have to figure out these options yourself. But notice how it's n equals 2, so I'm only choosing 2 numbers. And these are all logically possible ways I could choose these 2 numbers, especially if there's with replacement. So I can choose 1 and 1, I can choose 1 and 3, 1 and 5, 1 and 7. I can do 3 and 1, 3 and 3, 3 and 5, 3 and 7, 5 and 1, 5 and 5, and so forth. So I can do all of those when I'm picking up 2 of these samples. Now, what does it mean to find the sample mean? It means find the average. So mean just means the average. So what is this? I already did the first 2 for you. It means I'm going to add those 2 numbers up, 1 and 1, those data sets, and that becomes 2, but I'm going to divide that then by 2. Why? Because that's how you find the mean. You divide by the number of numbers. How many numbers? 2. Okay? You divide by the number of numbers. So there's 2 numbers here. I divide by 2, but 1 plus 1 is 2. Divided by 2 equals 1. I have 1 plus 3 equals 4, but then I divide by the number of numbers, which is 2. 4 divided by 2 is 2. So if I continued this strand, what would happen, guys, is I would take 1 plus 5 equals 6. Divided by 2 gives me 3. I would take 1 plus 7 equals 8. Divided by 2 gives me 4. And I would continue this all the way through. Okay? So here are the rest of them as shown. So what this means is I didn't show you the work because I feel like this is just sufficient work to show you. All I did was I took these 2 numbers, added them, and then I divided by 2. I took 3 plus 1, added it, that's 4, divided by 2. So you'll start to see a lot of these numbers repeating here. But what this tells us is this is my mean. Okay, these are my means, my sample means, all of them, all 16 of them. Okay, so as we continue, we now want to construct the probability distribution because this is all what it is. Remember, how do I construct a probability distribution? I take the number of times I see that number, and then I divide it by the total number of numbers. So the total number of numbers is 16, and I look at this. This is F. This means frequency. So F means frequency, which tells me how many times that number occurs. So look at our graph right here, where my pen is. How many times does the number 1 occur? Count. Well, there's no 1s over here. There's no 1s right here. There is a 1 right here. Okay, so since there is a 1 right here, I'm going to say that there's 1, number 1. There's 1, number 1. I then take that 1, that frequency, divide it by the number of numbers that I had, number of sample means, the number of sample means I've had, which is 16. I had 16 total sample means, and then I get a probability. Okay, that's what it is. Next, I take 2. How many 2s do I see? Well, I see this right here, and then I see this one. So that's 2 2s. There's nothing over 2 here. So there's 2 2s. I take 2, divide it by the number of numbers I have, which is 16 total. This is 16. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 times 2, because there's the same thing, 8 over here, 16. So let's begin this process. How many 3s do I have? Okay, I'm going to start crossing them out here. How many 3s do I have? 1, 2, 3. So I have 3 3s. So I'm going to write 3 3s. How many 4s do I have? 1, 2, 3, 4. I have 4s. 4 4s. How many 5s do I have? Well, I have 1, and then 2, and then 3 5s. How many 6s do I have? 1, 2. Okay? And how many 7s do I have? Just 1. Now notice this. This is amazing. Watch. Notice if I graph this, it goes up from 1, 2, 3, 4, and then it goes right back down. 3, 2, 1. That is normally distributed. What it would do, guys, it would be 1, 1, and then 2, and then 3, and then 4. If I graph this, it would be 1, 2, 3, 4, and then after that, it would go down 3, 2, 1. Okay, this is a normally distributed graph. Okay, but that's what we're trying to do. We're trying to make it normally distributed. We're trying to take the sample and normally distribute it so that we can perform data values on it. And so that's pretty cool, right? So now let's use what we're given here, and I want you to try to find the probability. Take these numbers, divide it by 16, and try to find the probability. So what is 3 divided by 16? What is 4 divided by 16? 3 divided by 16, and then 2 divided by 16, and then 1 divided by 16. Now, the cool thing is I already know what 1 divided by 16 is. Okay, it's 0.0625. I already know what 2 divided by 16 is. It's 0.1250. I should already know what 4 divided by 16 is, which is 1/4, which is just 0.25. Okay, which is 0.25. Now, what is 3 divided by 16? 3 divided by 16 is going to be 0.1875. And that's going to go right down here too. So 1875. Let me erase that real quick. So 18 and then 75. Perfect. Okay, so this is what I've done. I've constructed what we call my probability distribution. This is what it is. This is my probability distribution of the sample means. Okay? And yes, Math Excel will ask you to do that. It will ask you to solve for these numbers. You need to actually click on those numbers, go through each one, find your means. After you find your means of each one, then you have to count the number of numbers, the number of times you find each of them. Okay, you only have options 1 through 7 here, so those are my only options. Those are the total number of means. How many times do these numbers show up over here? You count them, then divide by the total number of numbers to total number of sets that we had, and we had 16 total number of sets for my samples. Okay, so it's pretty tedious. I get that. It is very tedious, which is why you're only going to have a couple of these on your homework. We obviously will have more different things that we need to go through in this lesson that your homework will cover. But these types of examples, you only have a couple. Now, we still need to do a variety of different things. We still need to find what my actual mean is. Okay? So what my actual mean is of not just my population, but my sample. Okay? My actual sample, the sample means. So I have all these means here. Okay? I have all these means. In fact, I'm actually just going to erase all this, and I'm going to rewrite the numbers down so that we're not confused with all the crossing out and everything like that. Okay. So I had 1, 2. This was 3, 4, 2, and then 3, 4, 5. This is 7, 6, 5, 4, 6, 5, 4, and then 3. So these were my numbers that I had, okay? Now, my population, I'm going to kind of recap. What did they say my population was? Well, they said my population, I'm just going to label this P1 equals, as a list, it was 1, 3, that's obnoxious, 3, 1, 3, 5, 7. Okay, that was my population. They told me a couple things. Ready? They told me my population mean was 4. They told me my variance, sigma squared, is 5. And they also said my standard deviation, my just regular sigma, was 2.24. Okay, that's what they said. They gave that to us. Now, what we want to know using my sample means is what is my sample? What is the sample mean of my sample means? I know that's kind of sounding odd here. Now, watch what's going to happen. I'm going to label this S of 1. Let me erase that. I'm going to label this S of 1. And I'm actually going to write out all these numbers. All these, because these are all my sample means, right? Those are all my sample means. Okay, those are my sample means that I found. So I'm going to list them all out. This is 1, 2, and then 3, 4, 2, 3, 4, 5. And then this is 3, 4, 5, 6, 4, 5, 6, and then 7. Okay, so those are all the numbers. It's about 16 total. Now, what we want to find is this. What is my sample mean of my sample means? Okay, what is the mean of my sample means? Okay, that's what it's saying. What is the mean of my sample means right here? What is the variance of my sample means? So notice how I'm doing sigma squared, but I'm doing an X bar here because that's going to signify the sample means. Okay, that's going to signify the sample here. Okay, and then I want to find my standard deviation of the sample means. How do I find these? If I'm given all this, I found this already with my table. How do I find this junk? That's when we use Desmos. So I'm going to go to Desmos. I'm going to show you what this is. So essentially, guys, recognize this one thing. You have this already. You already have this in your Google Classroom. If you go to Google Classroom, this data sheet that I'm about to use, 5.4a, is down at the bottom. Okay, it's on the Desmos links for statistics. If you view the material, you'll see 5.4a sampling distributions. You're going to click on that. This is going to help you solve a lot of questions on your homework if you use it correctly. So I'm going to teach you how to use it. Now notice this is example 1.1. We are on 1.1. And so far what we need is this information. They've given us this. We have found all of these, the sample means, using our table. Now, what is the mean of my sample mean? What is the standard deviation of my sample mean right here? And what is the variance of my sample mean? How do I find that? Well, all I have to do is just click on this, and then it's going to be given to me. But watch, this list is my population. Pretty cool, right? So this list is my population right here. 1, 3, 5, 7. Watch this. This calculator is cool because it already calculates the population of my mean. But this is already what they give us. It already calculates the population. That's what the P is there for, var P. So the variance of the population of these numbers. So the variance of the population is 5. But they already gave that to us, right? What this is saying, guys, this is my mu. This right here is my sigma squared, and this right here is my sigma, okay? So they already gave us this. I just think it's cool that we can find it also in Desmos, all right? Now, what are we interested in? We're interested in this. Ready? We're interested in this. Once we find, using this table, once we find all the means of my sample, it is fairly straightforward in that I just now need to go here on Desmos and type those numbers in. What numbers? The 16 numbers, okay? The 16 numbers right here, these 16 numbers I've listed out, all of these, where my mouse is, all of those numbers, those are the numbers that I type in here. I've already typed them in for you, okay? Keep the brackets and everything. The calculator will do all the work. I've already typed it in for you. Notice how it's 16 elements. Notice how we said there was 16 samples here. We got 16 samples by doing 4 squared because there's 4 possible population values, and then we want n equals 2, a sample size of 2. So we're selecting 2 out. That's n equals 2. So 4 squared, or 4 times 4, that gives us 16. Those 16 numbers for my samples, for my sample means, we listed out, and they're listed right here as well. We want to find the mean of my sample means. What is that? 4. It already does it for you. Okay? It already does it for you. Boom. 2.5. 1.8. That's it. So what does that mean? That means these values here are as follows. They literally are listed right here. 4, 2.5, and then 1.58. 4, 2.5, and then 1.58. So then I start listing them down. 4, 2.5, and then 1.58. Now, the notes will also say interpret. So what does this mean? So if I wanted to interpret this, what does this mean? Well, clearly watch. And this is the important part of this whole lesson. What is happening here? Look at that mean and then look at this mean. Are they equal? Yes, they are actually equal. And then the variance is actually very, very similar to the standard deviation of my population. So the variance of the sample means is very similar to the standard deviation right here of my population. But also notice that my variance right here, the variance of my population is 5, and then the variance of my sample means is 2.5. So it's actually 1/2. It's actually like times by like 1/2. So I take this by 1/2, and then I get that. Okay, so very, very interesting indeed. Think about that. We're going to do another example, but that's done. These are my answers. So, okay, what I'm trying to find is not only my sample means, which are these. These are my sample means. I've found these already. So that was my first answer. But I also wanted to find the mean of my sample means right here. The variance of my sample means right here. The standard deviation of my sample means right there. How do I find that? Using Desmos. I just plug it in. Okay? Plug it in. So I already had them listed out for you, so that was really nice. So example 1.2. So example 1.2. I'm going to list out all of the possible samples of n equals 2 again from the population of 1, 3, and 5. So instead of 1, 3, 5, and 7, I'm just doing 1, 3, and 5. Okay, calculate the mean and variance of the standard deviation of the sample mean. So now what it's asking is find the population. Okay, find the population. So that is going to be equal to mu. So once it's to find the population of the mean, my sigma squared for variance, and then my standard deviation, which is just sigma. Okay, that's what it wants us to find. Now we're going to compare the mean, variance, and standard deviation of the sample means. What does that mean? So my mean right here is my sigma with x bar. This is, mu with x bar. This is sigma squared with x bar, my variance, and this is just sigma x bar. So I'm going to compare those two. So this is a little bit more tricky because we actually need to find the mean, variance, and standard deviation of the population first. And then once we find the sample means of n equals 2 of all those samples, once we find the means, we list them together, and then we find the actual standard deviation, variance, and mean of the sample means. Okay, so First of all, form all possible samples of size 2 and find the mean of each. We then want to find the probability distribution, or rather make the probability distribution of the sample means, just like in the last example, and then find the mean, variance, and standard deviation, just like in the last example. How do I do that? Okay, I'm going to show you, and then compare them, of course. So, given the same kind of chart, I want to see if you guys can do them yourself. So I'll give you kind of a chance to do that. Remember that we have 1, 3, and 5. My population down here. Okay, I'll kind of write this out. My population was given to us as follows. Okay, my actual list was like P1. Okay, or rather, let's do this P2 because this is example 1.2. So this is P2 equals, my list was 1, 3, and 5. I need to find a couple things here. My mean, I need to find my variance, and I need to find my standard deviation. I don't know what those are yet. I'm going to show you what they are in a little bit. Okay, well, let's focus on this first. Now that we know that these are 3, okay, think about it. Fundamental counting principle, this is 3, and since I want size of n equals 2, I take, with replacement, I can do 3 times 3. So with replacement, because I can take them out and then put them back, take them out and put them back, I have 3 times 3. So this actually equals 9, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So you know that there's going to be 9 different solutions here, 9 different samples that you can have. And they are with replacement because 5 and 3 is the same thing as 3 and 5 right here. That's just true, right? 5 and 1 is the same thing as 1 and 5. So that's why it's with replacement, and that's how I know it is 9 different total numbers. I take 3, because it's 1, 2, 3, 3 numbers, times itself twice because it's with replacement. But I do it to itself. So I have 2 different 3's here because n equals 2. My sample size is 2. In other words, if that confuses you, just do 3 squared. You still get 9, just like in the last example. So my sample mean, what do? I add these 2 numbers up. So I add them. That's what I do. And then I divide by the number of numbers, okay, which is just 2 in this case. So 1 plus 1 right here is 2, divided by the number of numbers, which is 2, so equals 1. This is 1 plus 3, which is 4, divided by 2, which equals 2. So go ahead and go to town on giving the next set of numbers. Pause the video if you need to, and hopefully we'll get the same thing. Find the means of this. Add them up, divide by 2. Add them up, divide by 2. Perfect. This is what you should get for your means. When I added them up, I divided by 2. 1 plus 5 is 6. Divided by 2 is 3. That's going to be 4. When I add them up, divided by 2 is 2. 3 plus 3 is 6, which divided by 2 is going to be 3, and so forth. Okay, 5 plus 5 is 10. Divided by 2 is 5. All right? So those are the means. Now, let's do the probability, and then let's get to the population and the actual sample means down here. So what is the probability? Remember, this is the frequency. How many times does that number occur over here? How many times does 1 right here occur in my sequence? It's just 1 time, right? So just 1. How many times does 2 occur? Well, 1, 2. So 1, 2. So it's going to be 2. How many times does 3 occur? 1, 2, 3. Almost forgot that. 3. How many times does 4 occur? 1, 2. And then how many times does 5 occur? Once. So notice how this is also normally distributed. It starts out 1, 2, and then 3 gets to your peak, and then it goes down. Okay? So it starts out 1, 2, and 3, and then it goes to 1. Okay? So it is normally distributed. What's my probability? Well, I take 2 divided by the number of numbers, the total number of numbers, which in this case is 9. I have 9 total sample means. So 2 divided by 9, I have 3 divided by 9, I have 4 divided by 9, and then I have 5 divided by 9. What all these equal are as follows. It's actually very simple. and then equals 0.333 and 0.222. Okay, so not bad, I think, right? Not bad. So those are my probabilities. They will probably ask you for that on Math Excel, so that's one thing that we already have done. Now, what we need to find is my population mean, variance, standard deviation, and so forth. But before that, I'm going to look at my sample means. My sample means, what do I have here? Okay, I have my sample means, S sub 2, let's just call it that. It doesn't matter what I call it, but let's just call it 2. I have 1, 2, 3, 2, 3, 4, 3, 4, and then 5. So I have 9 numbers, and I just got them from right here. I also want to find my mean of the sample means. I also want to find the variance of the sample means. I also want to find the standard deviation of the sample means. How do I find those numbers? I'll show you how. Okay, right now. I go back here, I go to example 1.2, and then notice how this is my population, and then these are my actual answers for my population. So my mean of my population, the variance of the population, and then my standard deviation of the population. So I'm going to actually take those numbers, I'm going to go back and write them in. So that's the first set of numbers. And these are just my populations here. Okay, so 3, 2.67, and then 1.63. So 3, 2.67, and then 1.63. Okay? So now, what are my sample means? What's the sample of my sample means? Let's find out. I scroll down, and then now what I see is I've listed them all out. These are all 9. It tells us it's 9-element list. And now what I do is do the exact same arithmetic operation. This is my standard deviation of my sample means. This is the variance of the sample means, and this is the mean of the sample means. Okay, so 3, 1.3, and then 1.15. So that's what I'm going to do. So 3, 1.3, and 1.15. So 3, 1.3, and then 1.15. And the interpretation is very easy. Again, this sample mean variance is similar to the variance of the population, but it's just split in half. And then also notice that these are equal, just like the probabilities, the properties have said. Okay, awesome. That's my final answers. These are my final answers, guys. These are my final answers all down here. I found my sample means. I found my probability distribution. You'll probably see a couple of these questions on your homework. They are tedious, but they don't necessarily take long. You just need to know exactly what to do one after the other. If you pay attention to this video, you shouldn't have any problem. Okay? Let's erase this and let's get started on the next example. So this example is one that you'll definitely see on Math Excel. Very, very similar, okay? What I'm going to be asked to be doing is finding the mean and standard deviation of the population, so not the variance, just the mean and standard deviation of the population, if the number of DVDs represented by each of the families, 3 families in the past month is 10, 14, and 3. And we want to use a sample size of 2. So the 3 families, 10, 14, and 3, okay, we have a sample size of 2. So that means n equals 2, which means how many samples am I going to have? How many samples am I going to have? Well, if I have 3 right here, that is going to be 3 and then squared. So that means I have 9 total samples that I'm going to be kind of dabbling in. And you will have to list them out. I will list them out right now for you, but you will have to list them out, okay? Now that you know that, find the mean and standard deviation of the population. They want us to find that. They'll also want us to find the samples, list all the samples out of the given sample size of that population, which we will find. I know there's 9 samples total, but we need to list out all of them and what they are. I'm going to show you that what it is. And then find the mean and standard deviation of the sampling distribution, which is just find the mean and standard deviation of the sample means. Okay? That's definitely not what I wanted. Okay, that's crazy. Isn't that pretty cool? I think that's pretty cool. Let's erase that. Okay. Wow. And then compare them to the mean and standard deviation of the population. All right? Fantastic. So let's go to the next slide and let's go through each one of these. A, B, C, and then D. Okay. So A, I want to find the mean and standard deviation of the population. So my population I'm going to list out here. I know what I had was P sub 3 because this is my third example, and I was given 10, 14, and then 2. Okay? Or sorry, not 2, 3. 10, 14, and then 3. Now I want to find what mu is and then what that is. Now we can find what my variance is, but we don't need to. Okay, in fact, since we don't need to find my variance, I'm not going to find it. I just want to find my standard deviation and my mean. Eventually, I will want to find with my sample here, my sample means, I will want to find, and I will list them out. Once I find my sample means, I'll list them out right here, just like in the previous examples. But I will want to find my mean of the sample means, and then the mean of the standard deviation of my sample means. Okay? So, first thing they want us to find is the mean and standard deviation of the population. Let's go to Desmos and do that so we can list them out. Okay? So I go to example 1.3 and I list them out right here. So this is my population. This is my mean. Okay, so 9. So I'm going to go over here and do 9. And then I go back and then I have my standard deviation about about 4.5. So about 4.546, something around there. Again, I could put my variance, but I don't necessarily need to. I only want this. That's what the problem asked for. So 4.546. So 4.546. Perfect. Now, my sample mean. We're going to get to this later. How do I get to that? I need to now find this. Now, that was A. So I'm going to actually label this was A. I want to find the mean and standard deviation. Now, B is saying list the samples with replacement of the given size for that population. This is actually B. It's already kind of given to you. Okay, this is B right here. Just listing them all out. I can have 10 and 10, 10 and 14, 10 and 3, 14 and 14, and so forth. I can list them all out and I get this. Now notice how there's 9 of them because I had 3 in my population and a sample size of 2. So 3 squared, 3 times 3 by itself, 2 3s, 3 times 3, 2 3s, 3 times 3 equals 9. So I'm trying to be really redundant here. Okay, what does this mean? This means I now want to find, once I know what the samples are, I want to find my sample mean. What does that mean? It means find the average. So what is 10 plus 10? Well, that's 20. How many numbers do I have? Well, that's 2. So that equals 10. Okay, so I find the average. So it's 10 plus 14. Divide by 2, that's your number. So go ahead and do that real quick. Find the average of 10 and 14. Find the average of 10 and 3. Find the average of 14, 14, and so forth. Perfect. This is what you should get. If you got that, fantastic. So these are all my sample means. I'm actually now going to list them all out. So this is 10. This is 12. 6.5. This is 14. 12. And then 8.5. 3. 6.5, and then 8.5. So these are all my sample means just listed out. I now want to find the mean. This is what C is. Okay, C. So this is A, that's B, this is C. I want to now find the mean of my sample means and the standard deviation of my sample means. Okay, but before we honestly do that, I also want to do a probability distribution because we need to be comfortable in doing these probability distributions. Okay, we need to be able to do that. So again, just to recap, how many threes do I have? That's what it means, frequency. How many threes do I have? Well, I have one. How many 6.5s do I have? Well, I have two here, 1 and 2. How many 8.5s do I have? I have two of them. How many 10s do I have? I have one. How many 12s do I have? I have one. How many, two. I have two, sorry. Man. Two. And how many 14s do I have? I have one. So what does this mean? This means I'm going to take my frequency, 1, divided by the total number of sample means I have, which is 9. I'm going to take this, 2 divided by 9. This is going to be 2 divided by 9, 1 divided by 9, 2 divided by 9, and this right here is 1 divided by 9. Okay? So do that real quick, and then you'll see the answers right now. Sweet. So these are my probabilities, and these are some of my answers. They may or may not ask for these probabilities, guys. They may or may not, but I like to do them just in case. Now, we have one last thing to do, and that is find the mean and standard deviation. Find the mean and standard deviation. How do I do that? Okay, well, I go to Desmos, of course. So right here, as you can see, I've listed them all out, all 9 numbers right here. 10, 14, 6.5, 12, 12. I've listed them all out. And now the calculator does the work for you. 9, 10.3, and then 3.2. I only care about the standard deviation and the mean. So that's all I'm going to write down. So I have 9, and then the standard deviation is 3.21. So I'm going to go over here. So 9, and then 3.21. And then if it asks you to interpret, it's literally the exact same thing that we have been saying before. My population mean equals my sample mean. The population mean will equal the mean of my sample means. Okay? Perfect. So now that we have all that taken care of, let's erase this and let's get into our next big topic called the central limit theorem. So the central limit theorem, what is it? It's a lot of stuff, so pay very close attention. If samples of size n, so it doesn't matter the size. It could be 100, 15, 5, it could be 30, whatever. If it's greater than 30 though, okay, where n is greater than 30, are drawn from any population with a mean and standard deviation sigma, population mean, and a standard deviation right here. Okay? What we would say then is that sampling distribution of sample means approximate what we call a normal distribution. And that's totally true, right? We can even see it with little numbers. When we did the probability distribution on the previous slides, we could see how it does kind of do a bell-shaped sort of curve. And that's the normal distribution. But now we can kind of bypass the probability distribution here, and we can just say if you are given n, a greater size. Now we just did like size like 3, size 3 or size 2. We didn't do anything too intense. But if you're given a greater size, 30 and above, at least 30, okay, where your population is mu, standard deviation is sigma, then the sampling distribution of the sample means approximate what we call a normal curve. We're going to flush this out in a little bit. But really, this means the greater the sample size, the better the approximation of the normal curve. This also means if the population itself is normally distributed, the sample distribution of the sample means is also normally distributed. Okay? So you really need these two things to take place. You either need your n to be greater than or equal to 30, and then it's therefore normally distributed, or the population itself is normally distributed. So you either have a sample size of n greater than 30, okay, and taken from a population, then that means your sampling distribution will approximate a normal curve, a normal distribution, or your population itself is already normally distributed, and so therefore the sampling distribution will be normally distributed. Okay? So, taking those two things, those are the most important things, we're now going to look at specific variables and what kind of math are we playing around with this. So in either case, the sampling distribution of the sample means has what we call an equal, has a mean equal to the population mean. Has a mean equal to the population mean. So what will that look like? Exactly what we have been doing in the last couple of slides. The mean of the sample means. What is that? It means this. Okay? This is the mean of the sample means. So this right here, this mean of the sample means is this. But this will equal, the mean of my sample means will actually equal my population mean. Okay? So we've already said that before. I'm not going to go over it too much right now since I've already went through it a little bit in detail previously. So let's continue this kind of, what other math are we going to do perform on this? We're going to also look at the standard deviation. So the sampling distribution of the sample means has a variance equal to 1 over n times the variance of the population standard deviation divided by the square root of n. So what does this look like? Well, this is the variance of the sample means. The variance of the sample means literally just looks like this. So it's sigma squared and then my x bar. This equals my standard deviation squared and then all over n. Okay, this is the variance of the sample means. Now, Desmos does this for us. Even when we are going to Desmos here and doing all this jazz, guys, really, Desmos was already calculating that for us in those calculations of variance and standard deviation. Okay, now we're going to learn how to do it by hand. The reason why I wanted to do Desmos here is because it's kind of tedious with doing it completely by hand, with giving a list and everything. We're now going to be given values instead of lists. When we're given lists, it's really tedious. I have to actually use Desmos to do that. But now what we're going to be doing is given just data, not data values, but actual like means and standard deviations. And we're just going to be using these formulas right here to find the rest. And this is very easy math because I can just plug it into the calculator, right? I don't need to do this by hand. So that's the variance of the sample means. We also are going to look at the standard deviation of the sample means, and that's going to be just this. So the standard deviation of my sample means, that's what that is, equals my sigma all over radical n. This is a very, very, very important formula, and we are going to be using that formula a lot. Okay, so keep that in mind. So the standard deviation, as before, of the sampling distribution of sample means is going to be x, or sigma sub x, or sigma sub x bar sometimes. I know the bar is not on there, but that's what it means, is also called the standard error of the mean. We've already explained this. They mean synonymously the exact same thing. If I say standard deviation of the sample means, that's fine. It also means the standard error of the mean. So sometimes Math Excel in these slides will ask you find the standard error. Well, the standard error is how much it deviates from the mean. That's the standard deviation. Okay? Fantastic. So before we get into examples, let's kind of solidify this home by using what we call graphs and use these graphs to kind of compare the population and the samples here. So look at these 4 graphs. I have on one side this, any population distribution, and then underneath I have the distribution of the sample means when n is greater than 30. Okay? And then on the second side I have the normal distribution, normal population distribution, and then also the distribution of the samples means of any n. What does this mean? Well, notice my two characteristics previously. I had two characteristics. Number one, it had to be greater than or equal to 30 in order to get a normal curve. Because what we're doing is we're performing math on the sample means. In order to do that math, though, it needs to be normally distributed, just like my probability distributions in the example 1.1, 1.2, 1.3. Okay? How it was kind of like this, just roughly. We never graphed it, but it was sort of like that when we got our probabilities. In order to do the work on the sample means, they need to be normally distributed. How do they become normally distributed? The first thing that it must meet, the central limit theorem, it must meet, is that the actual sample size needs to be greater than 30. Okay? Because what if you have a population like Phoenix, for one, a population like Phoenix that doesn't look very pretty, that does not look very normally distributed, where you when you're kind of taking the data polls, it's very lopsided on one side rather than the other. It's not pretty, and sometimes data in the real world is not pretty, right? And so it's going to look like this, and your standard deviation is going to be like, blah, and then your mean is going to be like, blah. It's going to be very gross, right? But if the sample size that you're taking, even if this is a gross population, any population distribution, okay? If this is gross, if you're taking a sample of 30 and above, it will equal a normal distribution. That's the first point, okay? And that's what I want to stress home, because sometimes these problems, when you go through these problems, you need to make sure they check either this one or the next one. Now, what's the next one? The next one is if the population is already normally distributed. Isn't that great? It's already normally distributed. It's nice. It's neat. If it's already normally distributed, guess what? Automatically, your sample means no matter what your n is, no matter what the size of n is, will also be normally distributed as such. Okay? And so you can either have this one check out in our problems. We can have n equals greater than 30. But what if n does not equal greater than 30? What if n is less than 30? What if it's size 4 or size 10 or size 29? How can I still perform the math of the sample means that I want to perform? Well, if it's not greater than 30, then you have to go to the next check mark and say, okay, well, if it's not greater than 30, is my population normally distributed? If it is, then you can continue down and perform your sample means calculations, which I'm going to show you in a little bit. If it's not, though, then you can't perform what we call the central limit theorem. We're actually going to touch a little bit on that next week. Okay? So what happens? Okay, what happens? Can we do normal distributions if both of these check marks both of these tests don't check out? If it's not greater than 30 and it's not normally distributed, what can we do? Because sometimes it's literally not normally distributed. My population isn't always pretty, and I'm only taking a small sample size. What can I do here? Well, what you can do is what we call confidence intervals, and we can be reasonably confident that certain means or certain data values fall in between a certain percentage or a certain confidence level. That's going to be next week, okay? But until then, we're going to be doing this. I hope that makes sense. Let's get through some examples here before we end. So, a cellular phone bill for residents. Cellular phone bills for residents of a city have a mean of $63 and a standard deviation of $11. What is that? So this right here is my population mean. Okay, so my population mean is $63 and my standard deviation is 11. I always like to label it on the side here. Okay, now we read on. Random samples of 100 cellular phone bills are drawn. What does that mean? That means n equals 100. Perfect. That's greater than 30, right? Are drawn from this population, and the mean of each is determined. We want to do and perform the following calculations. Find the mean and standard deviation of the mean of the sample. And then what we want to find is sketch the graph of the sampling distribution of the sample means. Okay, now we want to sketch the graph of the sampling distribution. Now this is the population graph, so I'm going to label that. Now it looks kind of gross, looks kind of like a blob. Now notice this is not normally distributed. It's not pretty, right? Which means we have to make sure, okay, if it's not pretty, the population is not normally distributed. It didn't even say that the population was normally distributed in my problem. So since that's the case, what are we to do? How can we find the sample means to perform and find the mean and standard deviation of the sample? Can we even do that? We can if one thing checks out. If the sample that we're taking is greater than 30, then it will be normally distributed, and then we can perform the math. So, question, is it greater than 30? And we say yes. We are taking a sample size of greater than 30, so now my sample mean will be normally distributed no matter what. So what's my first step here? Well, A, find the mean and standard deviation of the mean of the sample. So A, my first step here is going to find my mean. So I want to find the sample, the mean of my sample means. I want to find the mean of my sample means right here. Now notice, if it's normally distributed, just like what we did in example 1.1, 1.2, 1.3 with the probability distributions, we noticed that they were equal. So the properties of sampling distributions, and given the central theorem, the central limit theorem, that should, give me 1 second. So given the central limit theorem, I have the mean of my sample means will equal the mean, that's what I want to find, of the mean of the sample, or sample mean. So the mean of my sample means will equal the population mean. So what's the population mean? They tell us in the problem, and that's 63. So that one is very simple indeed. Okay, that's the very first thing I want to find. That's my first step. My second step is to find, the standard deviation. So I want to find the standard deviation here. So that's the second step. Okay, so let's do the second step here. What's my formula for that? My formula is this. Remember how I said it was very important? So I'm going to rewrite it. So now, what is my standard deviation? Well, it tells us in the problem this is going to be 11. And then what is my n? Well, that's 100. So square root of 100. This equals 11 all over. Square root of 100 is 10. And that will equal 1.1. So that right here is the standard deviation of my sample means. And again, I can do this because though my population is not normally distributed, and it didn't tell us that, I can still find these values because my n is greater than 30. Okay, so it follows the rules of the central limit theorem, which means this formula will apply to find my standard deviation of the mean of the sample, and also the mean of the means of the sample. The mean of the mean of the sample. I know it's kind of confusing. Just say the mean of the sample means. How about that? I can find the mean of my sample means. Okay? Perfect. So then it's going to ask you, B, sketch the graph. And the graph will look something like this. Okay? So the graph will look something like this, where it's just 63 in the middle, but it's normally distributed. And it has an n equals 100. I know it's kind of hard to see there, but this is really what it is. Very simple, basic graph. On Math Excel, you're just going to click A, B, C, or D. But make sure it's just your mean is in the middle. So your mean of 63 right here is down the middle. So this actually equals your mean. But more importantly, the distribution of your sample mean. So this is the mean of your sample means right here. So your mu sub x bar. And then your standard deviation of 11. So standard deviation of 11. Okay, so Again, on Math Excel, it's just going to be A, B, or C thing. That's it. Now, let's continue. What if I continue with the same data? So I'm going to use the same things from example 2.1, but now I'm going to not do a sample of 100. I'm going to do a sample of 64. Okay? I'm still going to find my, wow. So I want to find the mean of my sample means right here, my x, or my mu sub x, or my mu sub x bar. These technically should have bars on them. And now I want to find the standard deviation of my sample means as well. Okay, those are just the two formulas that we showed when we went through the central limit theorem. At the same time, I want to find if n is greater than 30, which it is. Right here, n is 64, so it is definitely greater than 30. Sketch a normal curve with those parameters, my sample, my mean of my sample means, and then my the standard deviation of my sample means. Okay, and of course I want to compare those with example 2.1, and yeah, so let's do it, or not. Let's do it right here. Okay, so what will this look like? Well, let's do A first. What is the mean of my sample means? Well, that's going to equal my population mean, and my population mean doesn't change. It was actually 63. So I'm going to continue that mean from the previous example. Okay. Now, the standard deviation of my population mean. What is that? Well, that's going to be my population standard deviation all over the square root of n. So this is my formula, just rewriting it. What's my standard deviation of the population? It's 11. And then what is my new n value? It is 64. So this equals 11 all over 8, which equals roughly, when you plug into the calculator, 1.375. 1.375. 1.375. Okay? Perfect. Now we want to sketch a graph. And so what the graph will basically just look like is this, just very, very basic. It will be normally distributed, of course, because that's why it's greater than 30. Where my mean, right here, the mean of my sample means will be 63. And then my standard deviation right here will be about 1.3 something. So it's going to be like 62 point something, or 61.7 or something like that, 61.6. Okay, but that's what it is. You don't necessarily need to write that though. It's going to be very simple as long as you know that that's your new mean, and that's the mean of your sample means right here that goes in the middle. Then you'll be fine. Compare that result to the last example. Well, in the last example, my standard deviation of the sample means was 64, of n equals 64. So this one was, in the last one, when n equals 64, let's just say that. When n equals 64, this was 1.375, right? And then this was n equals 64, and then n equals 100 in the last one. My standard deviation of the sample means was 1.1. Now here's the interesting part. Which one's greater? Well, clearly this one's greater. So this one is greater. But why? Think about it. If you have a greater sample, if you are literally pulling out 100 people, 100 samples, do you think your data is going to be more spread out? No, because it doesn't need to cover as much, right? It's actually going to be a lot tighter, so a lot more close together. It's going to be smaller. It's going to be 1.1. Whereas your data, if it's going to be less than a big number, let's just say like 64, your standard deviation is going to actually be like pretty big because it needs to cover a lot more data. Okay, so think about that as we go through the next couple of examples. We have these last two examples, and then we are going to be done. So assuming the training heart rates of a 20-year-old athlete, if all 20-year-old athletes are normally distributed. So watch what it says here. it says that these are normally distributed. So that means my population is normally distributed. So my mean is 135. So at the bottom here, I'm going to say my population mean is 135. And then my standard deviation of the population is 18 beats per minute. So it's 18 beats per minute. So as shown in the figure, I'm gonna show that figure to you in a. Let's just show you now. I'm gonna actually erase all that. It's shown here. I'm all over the place. I apologize. So this is my population. Let's just put it up here. So my population mean is 135, and then my standard deviation of the population is 18. Okay, perfect. Fantastic. Now, I have that. Now I'm normally distributed, which you see is normally distributed. It's not rough at all like our other examples. The random samples of size 4. Now that's definitely not greater than 30, right? I want to know random samples of size 4, and I want to find the mean of each sample. Okay, the mean of each sample, of the sample mean. So I want to find the mean of each sample. Okay, and also the standard deviation of the samples. So I need to find the mean of my sample means, and I also need to find the standard deviation of my sample means. So I need to find this, okay, and then I need to find this, just like before. So A, I need to find the mean of my sample means, or my sample mean in general. If I have size 4, if my sample is size 4, does it matter if it's greater than or equal to 30? No, because in the problem they already told you it was normally distributed. So since they already told you your population was normally distributed, you're going to assume that your sample then is normally distributed. Because if your whole population is normally distributed and you take from the sample, you take from the population to get a sample, and the sample is a subset, you will be normally distributed. The samples that make up the population will be normally distributed already. So I don't care if this is greater than a 30, right? Which means, either way, even if it was greater than or equal to 30, your sample mean is going to equal your population mean. If your population mean is 135, your sample mean is 135. Now, what is your sample standard deviation? The standard deviation of your sample means. What is that? Okay, well, I'm going to be using this formula again, radical n. What's the population standard deviation? 18. What's my sample size? 4. So what is that? It's 18 all over 2, which is 9. And that's it. Okay, this is technically 9 beats and then per minute too. Okay, and this is beats per minute. So I have a mean of beats per minute, and I have standard deviation of 9 beats per minute. Okay, B does want you to sketch it, but the sketch is really easy, guys, because all it really is just make sure you sketch it, and then this is just 135. That's really all it is, with n equals 4. Okay, it's going to look almost exactly like this, your population normally distributed chart. Okay, awesome. Let's erase this. Let's go to our very, very last example. See, it's the exact same thing. All right, so where am I? Okay, so the heights of a fully grown white oak tree are normally distributed. So notice how it's normally distributed. So do I care if my sample size is greater than 30? I don't. Normally distributed with a mean of 3.5. So I'm going to put that up here. So my population is 3.5 as a mean. My population standard deviation is 0.2. Okay, and shown in the following graph, which I don't have. Fantastic. That's okay. It doesn't matter. Random samples of size 16 are going to be drawn from this population, and the mean of each sample is determined. Okay, so I want to find the exact same thing. I want to find what this is, my sample mean, and that's just going to equal my population mean, which is just going to be 3.5. Okay, now I also want to find my sample standard deviation. That's going to be 0.2 all over radical 16, because that's my n. Sorry, I'm going to just erase. I don't know what I'm thinking. 16. And so this right here, that's going to be 16. When I complete this, this is going to be 0.05. And I can just complete that on Desmos, use a calculator. Simple as that. Okay. My B is just going to be a very basic graph, guys. Just very, very basic. That's just going to be 3.5 as my mean, and then this is size 16. So it's going to be very obvious which one it's going to be. Awesome. So that is basically sample distributions and how populations can relate to your samples. How populations can relate to your samples. So if you take a sample distribution, let's erase this and get to the summary. If you take a sample distribution, you can verify their properties a number of ways, and then you can also interpret the central limit theorem using those properties, that your mean of the sample will equal your population of the sample if it's increasingly high, like greater than 30, or if the population is already normally distributed, and then, of course, your sample will then be normally distributed. Okay? So, closure, you will have a homework quiz tomorrow. It's going to be optional, though, so remember that. It's just going to be optional. Now it's all optional, all across the board, even if you don't have an A. So if you don't have time to take it, you don't need to take it. But tonight, during the homework, if you have any questions, please email me. But until next time, guys, this is C Squared Mathematics. I'm Mr. Carlson. Be sure to like and subscribe. Peace out.